Hello, everyone. Welcome back to our second lecture on quantitative data analysis, machine learning in finance and economics. And we are going to start this lecture by talking about the bias variance trade-off. And then we are going to move towards ridge regression. There will be three blocks for this lecture too. So let's start our first block. So in this first block, I'm going to talk about the bias variance trade-off, the James Stein estimator, a Bayesian interpretation of shrinkage, and start with rigid regression. Okay. There are a couple of references about the James Stein estimator and a very good introduction to rigid regression, some lecture notes that you can download from arXiv, and of course our textbook by Hasty Friedman, Tibishirani and Friedman. Okay? So let's start with the origins of shrinkage. Why in one day we thought about using shrinkage? Okay, why it's popular? So let's refresh our mind about the linear regression model. So we have a single equation, predictive linear model. So y depends on a constant plus a set of p regressors. So y beta naught plus beta x plus u. U is the zero mean innovation or error term, okay, or noise, call it as you prefer. And the number of variables depends on the sample size. I have mentioned that to you during our first lecture. So in fact, when I say P is P of T, T is the sample size. Without loss of generality, we are going to set beta not equal to 0. So we are assuming that we have the mean data. Okay? And also, all the explanatory variables are in the same scale. So we have standardized the variables. So think about dividing all your regressors by the standard deviation. And of course, we want to estimate the parameters. So how we are going to estimate the parameters, especially in situations where the number of parameters to be estimated is much larger than the number of observations, okay? And once we have an estimator, what are going to be the properties of this estimated model? We can write the linear regression in matrix notation. So just stack all your observations and in a vector form or matrix form. So we have y equals x beta plus u, okay? And we know that if the rank of x prime x equals to p, we have the OLS estimator that's defined by beta hat that you can see on your screens, okay? The problem is that this rank condition is not going to be satisfied when p is larger than t, okay? And solutions for that, I mentioned these sort of solutions during our first meeting, is to use penalization, regularization, penalize least squares. So what we have the sum of squared errors here. That's the usual cost function that we have for linear regression models, and we are augmenting this cost function by our regularization term. Call this the regularization term. Okay? And as I mentioned, this penalty term, this regularization term, is a non-negative function that depends on this regularization parameter lambda that controls the amount of penalty that we have. The larger the lambda, the higher the penalty, okay? And we have some examples of penalty that we saw also last week in our first meeting, okay? So as I mentioned, lambda controls the number of parameters in the model. If lambda diverges to infinite, no variables enter the model. If lambda converges to 0, it's just an OLS estimator. Okay, so we have this balance between fit and complexity. Okay, So what's the idea? What do you know? We know that, learned last week, that the conditional mean is optimal in the mean squared error sense. Okay? It minimizes the mean squared error, the MSE. Okay? And you also know that under certain conditions, OLS, whenever it's possible to estimate parameters by OLS, it's an unbiased estimator, and it's also the optimal linear predictor. Okay? It minimizes the sum of squared errors of all possible unbiased linear predictors. Okay? So you may think about this in a case where you have low bias, low variance. And you can compare to other models where you have low bias but high variance. Okay? So when the bias is 0, we know that whenever it's possible, the best thing to do is to do OLS, because it's unbiased. So among all the unbiased estimators, OLS is the optimal estimator. But now let's consider the case where we have bias. So we have a bias, so we miss the target. We have a bias. But there are two cases. One with low variance and another one with high variance. This one here we really don't want, because it's something that missed the target and spread all over, right? But imagine a situation where you have somehow something that's precise in a way that has low variance, but it has a tiny bias. So you allow for bias, some bias, but this bias compensates the amount of variance. So you want something that increase the bias but you decrease the variance, and as you all know, there's this relation between the mean squared error, the composition of the mean squared error, as equals to variance plus squared bias. So if we manage to increase the bias but decrease the variance, will it be possible to have another estimator with lower MSE than, for instance, ordinary least squares? So that's the trick of shrinkage. And the idea is that, for instance, here it's summarized in this picture. So you have here the values of lambda. That's the amount of penalty, the amount of regularization, the amount of shrinkage that you have. Here you have mean squared error. So for the OLS, it's invariant to the choice of lambda. OLS is fixed, and that's the MSE. And it has no bias at all. It's an unbiased estimator. Okay? But now, imagine that so if you look at here at bias, it's 0. So this MSE, if you look at the compositions in terms of variance and squared bias, OLS has no bias. So it's 0. So all this MSE comes from the variance. It's pure variance. Now let's do the following. Let's start increasing the bias in a way that we decrease the variance. And here we have the MSE. So if it's possible to do something like that, so if we can decrease the MSE because we are increasing the bias, but this increasing the bias is compensated by a decrease in the variance. Okay? So it starts to decrease and then it goes again and eventually explodes. But there is an amount of regularization, let's say lambda star, that's optimal in terms of MSE. So we will be willing to allow for some bias if it's not too big, that will be compensated by a decrease in the variance such a way that the MSE decreases. So that's the trick. Okay? So let's, what's the James-Stein estimator and the origins of shrinkage? So take a random variable x, okay, a sample of random variables. So you have like a sample of t random variables. They are all independent and they are all distributed as a normal variable, but with specific mean. So it's mu t. So each random variable, okay, has a specific mean, okay, and all of them have the same variance, unit variance. Let's assume that we know the variance, but we don't know mu t, okay. Problem: estimate mu t when the variance is known, okay. Loss function that we want to do that, squared error loss. So we're going to choose mu t hat that minimizes the risk. So the expectation of the square difference between mu hat and mu. Bear in mind that we have t here. Why? Because we have variable specific means. Okay? So a natural estimator, if we assume that you know that the distribution is normal, we can write the likelihood function, and the maximum likelihood estimator, mu hat, will be just xt. Okay? Just the random variable indexed by t. Very simple to derive. I invite you, if you wish, to derive this estimator. Just write the likelihood function and take the derivatives equals to 0, and you're going to get the estimator. Okay? Problem is what independently James and Stein, there are two different researchers. What they show is that this maximum likelihood estimator is not admissible when the sample size is equal or greater than 3. What is an estimator not being admissible? There is another estimator, mu tilde, such that the risk of mu tilde will be less or equal than mu hat. So basically we're saying that we can improve our estimator for the specific loss that we have chosen. Okay? So what James and Stein, they proposed that there's a way to overcome that. So the new estimator, the new mu hat, the James-Stein estimator of mu will be xt, but multiplied by this term here. And what is this term? It's 1 minus this ratio. That's the number of observations minus 2 divided by s squared. Okay? And what is s squared? Is the sum of the squared random variables. So basically here we are attenuating our estimator. We are shrinking this estimator. Okay? It's decreasing. So the James-Stein estimator will be smaller than the maximum likelihood estimator. So we are shrinking. And something for you to think about, and we can discuss during our live meeting on Friday. The sample is independent. The variables are independent. The independent sample, where each variable has its own mean. So, is it natural that including observations of the other variables, because now here we include the observations of all the other variables. When including this information, it improves the estimator. What is the explanation for this contradiction? Because it's a variable specific parameter, and we are saying that, okay, look at the other variables, and we can improve the estimator. Think a bit about it. We can discuss this on Friday. It will be an interesting discussion, but I will let you think a little bit about the problem. Okay, but this is the James-Stein estimator. So that's one of the origins of this whole boom of shrinkage estimator in statistics. Okay, so what's also the Bayesian interpretation for that? So imagine now that you have another sample of t random variable x, but now these variables are IID, normal, with constant mean mu, so the mean now is common to all the variables, and known variance 1. Let's assume a prior for mu. Let's assume that we have a prior, that's p, and this prior p is indexed by a parameter, let's call it lambda. Okay? The Bayes rule says that the posterior of mu, so the probability of mu given the data, equals to the likelihood times the prior divided by the probability of the data. Right, but our likelihood is Gaussian because that's what I assumed in our first bullet point. So this ratio is given by that expression that you see on your screens. Okay? So we can take logs. So we have log posterior will be a constant. That will be the log of the probability of the data. So it does not depend on mu. Minus 1/2 the sum of the square errors plus the log prior. If we assume that our prior is Gaussian with 0 mean and variance sigma square, that's our estimator. So the log likelihood is minus the sum of square minus a penalty term that depends on the square parameter that we have estimated. Does it look familiar? I'll give a hint. Rich. So there's a relation between shrinkage and Bayesian statistics. We are going to discuss a lot about that over the course. Okay? Right, so the Ridge estimator, see, that we saw last week is defined exactly the sum of squares plus the penalty term, which is a square penalty term. Okay? And it shrinks towards to 0. We're going to see that not exactly to 0, but shrinks the parameters towards to 0. Lambda is the parameter to be chosen. We are going to discuss today how to choose lambda, okay? And it has closed form solution. You can easily derive the solution of the Ridge problem, okay? And it's very good for prediction, not too good for variable selection, and we're going also to discuss this. So that's for our first block. See you during our second block.